instance of the toxins because there are too many formulas in here. So in the previous time we talked about the quantum field theory, how we can obtain the amplitude from the Feynman diagram. And in the Tuesday before, we also talk about what is the particle physics. They described what is the particles, elementary particle, and what is the interaction. And also we talk about some several types of particle with the several type of the charge, and their charge determine how they interact with the other particle by exchanging with the both carrier particle. So today I want to talk about the how can we construct the Lagrangian in the field theory, and we can lead off the Lagrangian to obtain the final law. So first of all, there are three types of the particle that are different with the charge assignment. So classifications are coming from the spin. So there are spin geo, 1/2, one particle. So this is a spin geo, scalar particle, and psi, spin 1/2, spin in particle, and spin 1 vector particle. Some such scalar spin vectors are terminology in the mathematics, but in the physics there are also other terminology for the scalar particle. There are scalar boson. Also there are spin, it's called a spin is a fermion, and the vector is something like gauge boson. We can construct the first of all free build for the spin geo 1/2. I constant if there are someone's in our lab, then we need to do nothing. We can describe the spin due to the spin 1/2, spin 1. There are spin geo 1/2 and there are some howling. We will turn off. Okay, very good. Right, so the pre-build. From the combining of the special relativity theory and the quantum mechanics, we can construct the pre-field Lagrangian. And first of all, it is a form of the Helmholtz equation. The Helmholtz equation means that there are some space-time propagation with the mass space. So in the three-dimensional spatial form is there are q plus m square. So suppose if there are some wave function quantum state, it satisfies this equation. So already we saw that such a form of the Helmholtz equation in many times. For example, the electromagnetic wave satisfy such an EM wave equation. And also in the quantum mechanics, the wave function in the wave mechanics, wave function satisfy the Schrödinger equation. So such Helmholtz equations describe the propagation of some physical object, and the solution is given by the plane wave with mass space, and it satisfies the dispersion relation with some energy corresponding to the time component and the momentum corresponding to the partial component. And in this time, the special relativity theory, the space-time is unified, so the Helmholtz equation should be described by the propagation of the space-time. So it becomes some partial skew plus m skew, where these partials mean that the space-time derivatives, also called some Darlang variation. So it contains the space derivatives and time derivative, and it is called the Klein-Gordon equation. So all the great fields, even whatever spin 0, spin 1, or spin 1, is satisfied by this Lagrangian equation as a all-dimensional space-time form of the Helmholtz equation. But in the spin 1/2 case, it is given by some Dirac equation, since to satisfy the Lorentz invariance. So the Dirac equation is given by this form. There are some additional gamma methods. Spinors are given by the Bohr component. So I want to talk about what's the spinor. There's some deep story in here. So first of all, such as spinors are coming from the Poincare symmetry. So one representation of the Poincare symmetry. So there's a Poincare groove which represents the space-time. So we can translate the space-time to rotate the space-time. And the rotation of the space-time means that we can choose two axes. The normal rotations are given by the choosing of the one spatial axis and the other spatial axis. But some special form of the rotation, for example, the Lorentz boost, it chooses the one times temporal axis and the one spatial axis. So such a Lorentz boost is a very special form which cannot shown in the classical regime. And yeah, so the point is Poincare grooves correspond to the space-time symmetry. So there's a rotation in space-time and translation, and corresponding to the such a symmetry, the rotation gives the angular momentum or spin or boost, and translation gives the momentum. So the representation of the Poincare group means that we should find the invariant representation. I mean the some of the invariant quantity under the such a space-time transformation of the Poincare group, and such invariant. Oh my, this is so it was a Tuesday, so the one meeting research meeting was cancelled in this Tuesday night, so I can do this. So the so invariant quantity under the space-time transformation of this Poincare group can be obtained by searching the Casimir operator, which is defines as these operators are committed with all other operator in the algebra. So we can obtain the two Casimir operators in the Poincare group. One is the mass, which is coming from the scale of the momentum operator, and the other one is the spin. So we can classify this particular state in terms of the mass and the spin because they are representation of the Poincare group or the space-time symmetry. And if we bind the spin representation, it allows the half integer and the integer spin. And the spinor is a spin 1/2 representation. And next, we want to obtain the Lagrangian for this spinor. And the one property of the Lagrangian, it should be the Lorentz invariant. If it is not Lorentz invariant, then there is a problem because the physics laws are different for each plane. So we need to make the Lagrangian as invariance, invariance and the Lorentz transformation, and to make the Lorentz invariant Lagrangian by using the spinor, we need to find how the spinor transform the Lorentz transformation. So the spinor transformation under the Lorentz, how spinor transform under the Lorentz transformation. So the spinors transforms with the spinor beside the transforms as some exponential I gamma some theta form, where the gamma is some mass gamma, there should be some sigma theta. So where the sigma theta corresponds to the infinitesimal small parameters and sigma corresponds to the commutators of the gamma matrix. So the transformation of the spin at the related with the generator sigma, which coming from the gamma matrix. So to construct the invariance, Lorentz invariant Lagrangian, we insert the gamma matrix because precise transformation of the spin precise always makes the term of the gamma matrix. So we need to add the gamma matrix. the to obtain the Lagrangian invariance Lagrangian by using the spinner. The one way is the psi bar psi, where the psi bars are defined as psi bars adjoint spinner, which it defines as a Hermitian conjugates of the spinner and the gamma zero matrix. And the other way is the psi bar and the psi with the gamma mu. This gives the vector, so that if we has the some vector which is space-time derivative and contrasts with this gamma matrix component, then we can obtain the scalar again. So that this is a Lorentz invariant scalar. If we give some coefficient for the scalar one, this thing, then we can bind the Lagrangian for the Dirac equation. So the point is we can construct the Lagrangian by using the spinner to make the Lorentz invariance, and this gives the Dirac equation, and it reduces the Klein-Gordon equation if we multiply the some additional term. So okay, now we obtain the spinner, and the final one is spin one, gauge boson, and also it has some Hartley multiplication form, but there are some other complexity. First of all, the vector field in the space-time is described by the Bohr degree of freedom, because there are the Bohr-dimensional space-time. But we know that the massless vector field or massless gauge boson has only the 2 degree of freedom of the polarization. So 2 degree of freedom should be the removed, and the one is eaten by the other field, and the one is the 1 degree of freedom that correspond to the gauge freedom. So there are some gauge redundant, which means that we can always choose the some pre-gauge parameters, and also we can choose some specific gauge. It's called the gauge fixing, and the point is the degree of freedom should be counted if if we consider the highest spin field. So also there are some massive gauge boson. In this case, the degree of freedom is 3 degree of freedom, so there are no gauge freedom. Always there is a gauge is already fixed. So if we obtain some equation for that, first of all, the equation is similar with the Klein-Gordon equation. So where is the Klein-Gordon? This is Klein-Gordon equation. So for the vector field, the equation of motion for the V vector fields are given by this Broca equation. Corresponding the Lagrangian is given by the partial squares a mu. Maybe so I can say the partial a mu squares and the m squares a squares with the 1/2. So we can construct the Lorentz invariant Lagrangian again for the vector field or gauge boson, and for case of the last case, the second sums are benefit. So this is for the free field case, but we want to add the interacting Lagrangian. In this case, we cannot obtain the exact solution. For the free field case, we can obtain the exact solution by that the exact solutions are given by just a plane wave with the mass space. But so we can construct the field operator by using the solution. So the field operators are constructed with the creation and annihilation operator, which is called the ladder operator. This is similar with the quantum simple harmonic oscillator. But in case of the interacting theory, we cannot obtain the exact solution. Someone tried to obtain the exact solution, but it's hard to obtain it mathematically. And so when we cannot obtain the exact solution, we always use the perturbation theory. If there are some small term in the Lagrangian or Hamiltonian, that is the one way in the quantum mechanics. So we use the perturbation theory, and we already discussed how can we obtain the amplitude, which is the probability amplitude from the initial state to the final state. But today my point is how can we construct the interacting Lagrangian? Also we want to consider the Lorentz invariance. So interacting Lagrangian, first of all we should count the mass dimension. So first of all the action is given by the integration of the Lagrangian over the space-time volume, and the action is a mass dimension 0, and the space-time volumes are mass dimension -4. So the Lagrangian has a mass dimension 4. So if we consider the Lagrangian, then we should all the terms should be the mass dimension of the 4. So for example, in the previous boy build case, first of all, I didn't Lagrangian for the scalar field. So there's a scalar field Lagrangian similar to the massive case boson. So for the scalar field, if we consider this one, mass dimension of the Lagrangian is 4. And this partial corresponds to the momentum in the operator regime in the quantum mechanics. So this is correspond to the mass dimension 2 because there is, so the pi shift the mass dimension 1. Similarly, in the mass term, there's a mass 2 and mass q. So that this gives us a mass dimension of the Lagrangian pole. So the scalar field has a mass dimension 1. Also, the vector field a mu has a mass dimension of the 2. But in the spinor case, it has a mass dimensions of the 3/2. Let's see that. So there is the momentum, one momentum. So there are mass dimension of the 1. So 2 halves the mass dimension of the 4 Lagrangian, the side shift the mass dimension of the 3. Also for the similar the mass term, this is connected to the mass term. So the mass dimension of the spinor shift is 3/2. So if we consider some Lorentz invariance Lagrangian with the mass dimension, the interacting Lagrangians given by only the small number of the form. So for example, we can consider some interaction between the scalar and the spinor. The scalar has the mass dimensions of the 1, and to make the Lorentz invariant scalar, the only possible way is the scalars, and the mass dimension is given by the pi is the mass dimension 1, and the besides the 3/2 and 3/2, so it gives a mass dimension of the 4. And also we can consider the interaction between the spin 0 particle and the spinor, and spin 1 particle. And if we consider the Lorentz invariance and the mass dimension, then there are pi and the 2 gauge boson a mu. And the other way also we can consider pi, some partial mu pi and a mu pi. That's the other way. Instead of using the gauge boson, we can insert the space-time derivatives as a momentum operator. This is actually a derivative coupling. And for the interaction between the spin 1/2 and the spin 1 gauge boson, gauge bosons are vectors, so that we should contract with the vectors. So we can construct the vector quantity, vector of that, by using the spinor with the gamma matrix. So the interaction between the spin 1 and spin 1/2 particle has such a form. And finally, there are one more thing. The scalar particle can self-interact. Lambda is actually this is a massive coupling, and high force. So maybe the mu is a better terminology. So mu is a massive coupling, and the lambda is a massless coupling here. So this is the possible interaction of the scalar spin 1/2 and the spin 1 gauge boson in the mass dimension of space-time. Also, we can extend the space-time dimension, then it allows some high dimensional operator, or we can just add some higher dimensional operator without the extender of the space-time dimension by using the some mass operation in the denominator, but such operators are surplus in the low energy regime. So that's some of the theme of the effective field theory. And also we can extend the spin of the particle. In the higher spin, for example, the graviton, it has a spin 2 in the general relativity theory. So that we can also coupling between the spin 0 and graviton spin 1/2 and graviton spin 1 and the graviton. So that is already we prepared all the things to like the standard model Lagrangian. So we already know that the all pre-built Lagrangian and the interacting Lagrangian. So first of all, for the scalar field, I will start to the scalar tension, and also the mass term of the scalar particles also contain the scalar potential, and this term interaction between the scalar particle and spin particle becomes equal coupling. And the interaction between the spin 1/2 particle and the scalar particle, spin 1 gauge boson and the scalar particles can be written by the covariant derivatives. So these covariant derivatives contains the space-time derivative for the kinetic term and some coupling term with the vector gauge boson. So this is called covariant derivative. So this d mu pi contains also the kinetic term for the scalar field. And similarly, kinetic term of the spinor field and the interaction between the spinor and the gauge boson can be combined with the covariant derivative. Also, we need to add the kinetic term of the massless gauge boson spin 1 field, and this is written by the 1/4 F mu. This F mu is the field strength, or this is same with the Maxwell tensor in the partial relativity theory for the electromagnetism. So this is given by the commutator of the partial mu, space-time derivatives and the gauge boson.